All right, so we're going to talk a little about magnetic fields on current carrying wires. So let's consider the equation we had for forces on charged particles a second ago, QV cross B. So I'm going to break down this V. How do you find velocity? Well, velocity is going to be how far something goes. It's distance, but I'm going to use length here, divided by the time, right? So it's going to be length over time cross product B. That's still equal to force. But this is just a scalar, right? And this is, well, I guess let's put our vector signs, vector, 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 vector. Yep, got all this. Okay. So this guy's just a scalar, and so is this. So doesn't matter where I put the scalar, I can move it around. So what if I move it just a little bit to the left and put it under the Q? I say force is equal to Q over T times L cross B. Have you guys caught the magic what I've done yet? What is charge over time? Or if charge is the thing flowing, right? So if we're looking at that, think back to circuits. Well, I know that Q over T, the charge over time, is going to be current. So I can replace this line in my equation with current. So that's going to tell me that force is equal to current times length cross B. So this is the direction the current is flowing. So we're going to get F equals IL cross B is my new formula we're going to use for current carrying wires. So if I have, let's say, a wire carrying a current going that way, so I have a vector, and let's put it in a magnetic field going out of the page. So let's put it in some dots. Which way is the force is going to feel? Well, we're going to use my right hand rule again. Same exact rule, except I'm going to take my velocity, which is my fingers, now becomes current. So let's take that guy and try and turn that into an I. So now my right hand rule is current on my fingers, force on my thumb, and magnetic field on my palm. So my magnetic field is going out of the page, so my palm pointing up, and my fingers pointing to the right. Let's see if I can make this fit. So it should be kind of like that. So my thumb points down, so that tells me my force should be downward. What about if you have a situation where you have your magnetic field goes this way, and you have a wire carrying current going that way? Well, same idea. My magnetic field, I'm going to try and put my palm in that direction, which is a little bit hard. And we're going to consider, so this is my theta, right? So I want to consider the perpendicular component of the magnetic field. So really I'll put my palm and consider the perpendicular part of the magnetic field. So that's B perpendicular. So that's going to be my palm points up, my fingers point to the right, and my thumb points out of the page. So that means my force is going to be upwards. So I could draw my force the same way I do magnetic fields with a little dot. Put it in a circle just so you guys can see it a little better. And then one more of these examples real quick. If my magnetic field is going like this, I'll draw my wire in red this time just so it's easier to see and stands out a little better. And my current goes that way. What's the force? Well, I can't put my hand in. There's no way to actually get my fingers and palm pointing like that, right? It doesn't work. But also, another way to think about it is that the sine of the angle is 180, or 0 if you'd rather. So we can say theta equals 180 degrees. So sine of theta, in this case, 0. But also you can just do it that I can't put my hand in that position at all. There's no possible way. So the force must be 0 because the right hand rule can't be applied. Yeah, I mean that's the gist on wires in a magnetic field. But the other thing that we need to know is that wires generate magnetic fields as well. Current carrying wires generate magnetic fields. So currents cause magnetic fields. So how's that look? Well, so if I have a wire that's running like this and a current going that way, then what direction is the magnetic field? Well, it's actually going to loop around the wire because magnetic fields are always go in loops if they can, except there's some special circumstances where they're not. But if you have like a bar magnet or a wire, it makes loops. And even those special circumstances are just like one of those things we approximate for physics. It doesn't actually do that. So it's going to come from behind the wire. It's going to loop in front of the wire and go back behind. So magnetic field is going to go like that. And then you're going to have, it's never in just one loop. You always have more. It's probably a good idea to try and draw 3 or so you can illustrate the pattern. And it's not going to fit, so I'm just going to kind of make it work. And it's going that way. So maybe it might be easier to say if I have a wire going vertically, right? There is my wire, current's going up. But it's kind of coming, imagine kind of out of the page. So I want to draw a plane that I want to draw this field on. So then the wire is going to poke through a hole in this plane. So it's going to poke through a hole there. So when I draw this field, it's going to circle around, pass in front, and go behind. You have another one, circle around, pass in front, go behind. And it can't really fit on the page because I didn't draw it big enough, I guess. You have another one that's going to be farther out. It's going to kind of fit on here and follow that pattern. Now it's important that it's farther out. Why is it important that it's farther out? Well, the equation for a magnetic field generated by a wire is going to be dictated by a law called Ampere's law, but we're not going to worry about the origins of the law yet. We'll get to that later. It's going to be the permeability of free space, which we've talked about a little before, divided by 2 pi times the distance you are from that wire. So let's write those down. So B is magnetic field, I is current. You guys should know that. Mu naught is equal to 4 pi times 10 to the negative 7. And it is the permeability of free space, or vacuum permeability, some people call it. SP. Wow. Okay, there we go. You know what I mean? And then R is the distance from the wire. So on this diagram, if I say I'm out here, one of the magnetic field strength there, that's my R. Okay, so that's the basics on magnetic fields from wires. We'll do another video shortly where we talk about how to apply it in other ways, but this is the basic concepts. All right, I'll see you guys next time.